Measurement is very important. In chemistry, there are a lot of things that we measure, and you need units to make measurements. And so we need to talk about units. There are two basic unit systems in use, what we call the metric system and the English system. The metric system is used in most of the world, and the English system is still used in the United States. We keep saying we're going to convert to metric, but we don't actually do it. We're just like playing around with it. What scientists use is called the International System of Units, or the SI system. This is based on the metric system, and there are very subtle differences between the two systems, but it mostly has to do with what the base units are. And as far as I'm concerned, the differences between the SI system and the metric system are really not worth talking about. And so I'm not going to emphasize those at all. I'm basically talking about the metric system. So here are units. These are the SI base units. Length is measured in meters, mass in kilograms, time in seconds, temperature in kelvins, amount of substance in moles. These two other quantities we don't use in this class, but electric current and luminous intensity. There they are. So let's think about some of these basic units. The meter. A meter measures length. I know some of you are not real comfortable with the metric system. I'm hoping to change your mind about it. Once you get used to it, it's so much easier to use than the English system. It's helpful to have an idea of how big these units are. A meter. We've heard the word meter, but if I quizzed you, how many people would actually know how long a meter is? I'd like you to have a clue. It's close to a yard. Because if we have a ballpark idea of how big these things are, it's helpful to us in our calculation. So a meter is a little bit longer than a yard. A yard is 36 inches. The meter is 39.37 inches. You don't have to memorize that. It's just there. Originally, the meter was defined as 1/10,000,000th of the distance from the equator to the North Pole going through Paris. That's real practical, isn't it? One of the things that the SI system did was redefine some of these base units. And it's now defined based on how far light travels in a certain amount of time. One of the important things to have in a system of units is a way to very precisely identify how long the unit is. The unit foot that we use, came about in very old times. It was the length of the king's foot. Well, what happens when the king dies and the next one has a different sized foot? How do you determine how long the foot is? Do you change it? Back in those days, it probably didn't matter that much, but now it matters a great deal. So we have very precise definitions of these things. A kilogram. This is for measuring mass. Mass and weight are not exactly the same thing. Weight is the pull of an object by gravity. It's a measure of how gravity pulls on an object. So because it's related to gravity, the gravitational field affects your weight. So if you're 100 pounds on Earth, you're not going to weigh 100 pounds on the moon. You're going to weigh about 1/6 of that. You can actually have a small difference in your weight even on the planet Earth if you go to different places on the Earth. The gravitational pull is slightly different, and so your weight is slightly different. Mass matters amount of substance. It's not related to gravity. So mass does not change whether you're here or on the moon or in outer space. The amount of stuff in your body is the same. So the SI unit is the kilogram. And a kilogram is just over 2 pounds. That's not so useful in chemistry because that's quite a bit of stuff, 2 pounds of stuff. These balances don't hold 2 pounds, and it would be very wasteful to do experiments with pounds of substance. So we use grams. And one of the cool things about the metric system is we can change the size of the unit just by putting a prefix in front. So the gram is a small unit and the kilogram is a big unit. We have different sized units in the English system as well. We have ounces and pounds and tons, right? You wouldn't measure the mass of a 6-year-old or the weight of a 6-year-old in tons. It'd be silly. The number would be way too small. You wouldn't want to measure his mass or weight in ounces either, because the number would be too large. We like to use a number that's similar, a unit. We like to use a unit that's similar in size to what we're measuring. If you're going to measure the length of this desk, you're probably going to use inches. If you're going to measure the length of the room, you'd probably use feet or yards. If you're going to measure the distance between Fresno and San Francisco, what would you use? Miles. You wouldn't want to use light years because that's way too big. So we need units that have different sizes. So in the metric system, we use prefixes like this to change the size of the unit, instead of just having new unit names. So 1 gram is 1/1000th of a kilogram. And we'll go over these metric units in more detail. Here on the balance here, we have a nickel, and a nickel weighs about 5 grams. So that gives you an idea of how big the gram is. It's a small unit of measure. Time, we don't really have a problem with time because the metric system also uses seconds. This measures the duration of event. The unit is second, and this is defined as a particular number of radiation events in cesium-133. Again, I'm not going to quiz you on those definitions. I just think it's kind of interesting to hear how these things are defined. Temperature. What do we use to measure temperature, like outside? Degrees Fahrenheit, right? And so we might say, oh, well, it was 40 degrees Fahrenheit when I left for work this morning. Or I'm looking at the thermometer here, and now it's 77 degrees Fahrenheit in here. That's too warm. In the metric system, the base unit is the Kelvin. Temperature is a measure of the amount of kinetic energy that a substance has. So remember I said that particles, even in the solid state, are not completely still. They're vibrating, just like all of you are moving a little bit. Temperature is a measure of the average amount of motion. So if all of you were to get really agitated and just be, oh man, like little kids when they have to go to the bathroom, you're just kind of jumping around in your seat when you're going to stop talking, I need to go, then your kinetic energy would go up. When a substance warms up, the particles move more, and we observe that as a rise in temperature. The measure of that is the Kelvin. We also use degrees Celsius, but the official unit is the Kelvin. Temperature also tells us which direction heat will flow. Thermal energy we call heat. Thermal energy will go from a higher temperature substance to a lower temperature substance. So the Kelvin scale and the Celsius scale are very much related, and I want you to understand how those relate to the Fahrenheit scale. The Fahrenheit scale, like I think many English units, came about kind of randomly by chance. Guy makes a thermometer and just sort of marks things. He actually based it on 0 being the lowest temperature he could achieve with a salt ice water solution. Well, that's not so useful anymore. But if you're wondering where he came up with 32, it had something to do with that. The Celsius scale is based on 0 being the temperature at which water freezes. That is a constant temperature given a given pressure. So water freezes at 0, water boils always at the same temperature too, 100 degrees. And so The Celsius scale is based on the boiling and the freezing point of water. Why? Because those are things that can be reproduced easily anywhere. A lot of these things, like the Celsius scale, were devised a long time ago, I think even before electricity was being used. So how do you make something and measure it? Well, if you have ice and water together, that's 0. You can make your own thermometer and calibrate it using an ice water bath and a bucket of boiling water. And so those were useful temperatures. The Kelvin scale has 0 being the lowest theoretically possible temperature. It's called absolute 0. And that would be analogous to the particles in the solid not moving at all. So for students, that'd be all of you frozen. You're not blinking, you're not breathing, your hearts aren't beating, you're all just like stone statues. That would be 0 Kelvin. They actually haven't been able to achieve 0 Kelvin. They've gotten really close, but they haven't achieved it yet. Between the boiling point and the freezing point of water on the Celsius scale are 100 divisions. Between boiling and freezing on the Kelvin scale are also 100 divisions. The Kelvin is the same size as the degree Celsius. The difference is that 0 is at a different point. The Fahrenheit scale has 180 divisions compared to the 100 divisions here. And so when we convert between these scales, we pretty much need to use equations. I'm going to stop here, and we'll get into this equation business on Wednesday.